This is a demonstration of conformal microstrip array design with FEKO and anten Magus. We will use the design of the antenna for a proximity fuse radar for an air defense missile as a case study. This antenna will have to satisfy the following specifications. It has to conform to the airframe of the missile. It must operate at 2.4 GHz. We want 10 dBi gain in the main lobe. Interference from side lobes have to be minimized. The main lobe should be able to squint 45 degrees forward to detect a target. We will start by performing the array synthesis in anten Magus before modeling the antenna in FEKO. Once the antenna is confirmed, we will mount it on the missile and simulate again to test if it works properly in the intended environment. Before we start our demonstration, it is instructive to understand what functionality is provided by the anten Magus array synthesis module. Anten Magus can be used to synthesize various types of array, including linear, planar, circular, and cylindrical arrays. Each array design can be customized in various ways. For example, linear arrays can be designed by specifying beam width, directivity, direction of main beam squint, and for end-fire operation or with a broadside null. Various array excitation distributions can be chosen, including uniform, Dolf-Chebyshev, Villeneuve, and Bayes. Array patterns can be combined with various radiating elements to estimate performance of the final array. We will start our demonstration by switching to the array synthesis mode in anten Magus. Array synthesis is performed in 3 stages. We will begin by synthesizing the distribution matrix. Our antenna will have to be a linear array, and we select this option from the array shape drop-down. The specification of our antenna includes details on both directivity and main lobe squint, so we select a broadside array with the option to specify the scan angle and excitation taper. Now click Setup. Next, we specify the operational requirements for our antenna. The center and display frequencies are both set to 2.4 GHz. The element spacing will be slightly less than half a wavelength. And we specify that the elements must be along the x-axis. We select the option to specify directivity in the main beam and enter our specified values of 10 dBi gain and a 45-degree scan angle. In radar applications, it is important to try and manage all side lobes at the same level, so we select Dolf-Chebyshev as our distribution taper and enter 30 dB as our side lobe level. Once we apply the design, our array pattern is immediately designed to our operation specification and the operation parameters displayed in the result window. The important output of this process is the location and excitation of the driven elements in the array. We can review these outputs by switching the distribution layout matrix view to its table mode. Position is provided in Cartesian coordinates, and the magnitude and phase of each radiating element is specified. The next step in our process is to design the element pattern. Since we want to make our antenna conformal and do not need a structure that transmits large amounts of power, we select a rectangular patch antenna as our radiating element, and we specify that it transmits in the Z direction in its isolated layout. We apply these requirements to demonstrate the element pattern. Our final check that the process is valid is to review the final predicted array performance. We switch to the Synthesized Array tab. The predicted array performs as expected, with main lobe pointing to 45 degrees and side lobe levels 30 dB down from the main lobe. Before we model the array in FEKO, let us first answer the question, why is FEKO modeling necessary? Anten Magus estimates antenna performance using array theory and not rigorous simulation methods. Antenna Magus thus ignores effects that may be important to the final antenna, including the effects of a finite ground plane and mutual coupling. A FEKO model will model all of these effects accurately, and if its answers compare favorably with the predictions of Antenna Magus, this will provide us with confidence that the eventual implementation will satisfy our requirements. Creating the geometry for a model of the microstrip array mounted on a finite ground plane is a simple task, utilizing the cuboid and rectangle geometry primitives in CAD FEKO. We will use FR4 as a substrate. At only 1.5 mm thickness, this presents a simulation challenge to integral equation-based simulation methods that discretize surfaces. We will use FEKO's powerful finite element differential equation-based simulation method to simulate this geometry. FEKO's implementations of the finite element method utilizes the FEBI method as a boundary condition to the finite element region, minimizing the dimensions required for this boundary. FEKO further accelerates this simulation by treating the integral equation boundary with a multilevel fast multipole method, which is unique in the electromagnetic simulation industry. Since Antenna Magus was used to design a planar antenna, we begin our investigation in FEKO by simulating this same planar antenna and comparing whether the FEKO output agrees with the Antenna Magus prediction of performance. We start by testing whether the required side lobe level has been met. A normalized Cartesian plot comparing results from the FEKO model in blue to the Antenna Magus prediction in red shows a good agreement between the two models and confirms that the antenna meets the required side lobe restriction. A polar plot comparing directivity of the FEKO model to the Antenna Magus model once again shows good agreement and confirms that both models predict a 45-degree squint angle. The planar FEKO model is thus performing as expected and can be modified to fit the conformal missile. We are now confident that the planar antenna model that was created in the previous steps of our design process is an accurate representation of the array that was designed with Antenna Magus. We can thus bend the antenna to its final conformal state. We are now looking at the model of the conformal antenna that was created in CAD FEKO. Please refer to the FEKO website for instructions on how to model a conformal antenna. The radius of curvature is clearly visible in the transparent front view on the bottom right, while the main view shows a 3D perspective of the antenna. The missile model was previously defined and is currently hidden in this model. Keep an eye on the radius of curvature view on the bottom right as the missile model is made visible. The front view with transparency clearly illustrates that the antenna is of the right curvature to fit exactly onto the missile body. Inspecting the full 3D view of the missile, it is clear that the missile body is electrically large with length roughly 27 wavelengths. The optimal full wave simulation method for the missile body is the multiple fast multipole method, or MLFMM. However, this is not the most optimal solution for the conformal antenna, which is best solved with a finite element method, or FEM. As we previously mentioned, FEKO was the first commercial software to include the finite element boundary integral, or FEBI technology. This technology is now used to bound the FEM region with a small airbox, while still using the MLFMM to solve the rest of the missile body. Note that the airbox is rather small, as it only has to surround the area of the model that we want to solve with a finite element method. This particular problem was solved on 2 quad-core CPUs in under 5 minutes, requiring less than 7 GB of RAM. The results of this simulation can easily be visualized in post-FEKO. A 3D view of the missile with a superimposed 3D depiction of the antenna's radiation pattern provides good qualitative evidence that the antenna is indeed radiating forward. 2D Cartesian and polar plots may be used to check the detail of the solution. Post-FEKO's intuitively easy-to-use measurement traces can be used to confirm that the main lobe is radiating as expected. A 14 dBi gain is realized with a squint angle of 43 degrees. It is also easy to confirm that the side lobe level is indeed under control, more than 24 dBs down from the main lobe. This concludes the demonstration. We have shown the following points during the demonstration. Anten Magus provides a wide range of array synthesis options, helping designers to quickly find the optimal excitation and geometry for a new array. Conformal antenna arrays are easily modeled in FEKO, with simulation results that compare very well with expected results. FEKO provides the industry-leading ML-FMM-FEM hybrid formulation, which is an optimal implementation of FEBI technology. This enables users to model complex antennas in the proximity of electrically large structures. FEKO is a powerful tool for antenna placement studies, confirming whether antennas will work as expected in their operating environments.